Hello, everyone. Good morning. I'm Olivier, and this is Georg, and we are presenting here from Lausanne. We are both PhD students at EPFL, and we will be talking about first-class type-level programming.
So what we'd like to tell you about in this talk is, well, sort of starting from the current state of metaprogramming in Scala 2, some reflections and then some new solutions that are upcoming. So before starting, I'll just remark that metaprogramming has been remarkably successful in Scala 2. Pretty much any library that you might have worked with is using macros or implicits or both in some form. And that's because they enable things that are not easy to do within the base language. I mean, they're doable with implicits, certainly, but perhaps not in the way that implicits were designed originally. And similarly for macros, this was also sort of supposed to be a better alternative to pure Java reflection and has grown into a very powerful tool, but one that is somewhat incomprehensible to people at times. So metaprogramming in Scala has had maybe a reputation of being not very accessible. And if you look at some of the most popular libraries in the space, say if you think about type-level programming that would perhaps be shapeless, this is something that's written by experts. There's a very small audience of people who can actually add functionality and modify it. And thus it's considered a bit scary perhaps by people, but it's turned out to be very useful. And so part of the vision for Scala 3 was to come up with more principled and more accessible solutions for metaprogramming. And really the core goal here is to make the common use cases easier so that more people can actually benefit from this and write their own customizations. And so the context for this talk in particular is that we'll be talking about type-level programming.
So this is the example we will try to, this is the problem we will try to solve today. So our example is a database query using Spark. So the code that you are seeing here uses the Spark API to load two files and then performs a join between these two tables. And what you can see here is that it uses string, so it's untyped in a way and unsafe. For instance, if you make a typo in the name of the key for the join, then you will get a failure at runtime. And so what's interesting here is you can see the return types over here. Everything is a data frame. This means that there is no static information about the layout of the tables or what's currently being computed. Everything happens at runtime, and it's quite unsafe. So, yes. Yeah, the schema you can see here, this is what you will get at runtime, these three columns. So after performing the join, you will obtain a table with name, age, and unit. And if you try to use that table afterwards, but you mess something up with a string or the number of columns, you will get a runtime error, which is quite annoying in Spark because Spark programs take a while to execute. And our goal for today is to be able to detect this type of error as early as possible and make this code type safe.
Right. So in particular, if you had to try to join on something other than name here, so some column that's not contained in both of the data frames, you would have gotten a runtime error right here already. And so this is something we'd like to catch early on. So what are current solutions for this? Well, one common idea of how this is currently solved, if you want to get compile time safety for this kind of API, is phantom types. So the idea of phantom types is to actually wrap this data frame in some other class that has an extra type parameter. And so this is going to be the phantom type. This is going to be a type parameter that's not actually used here anywhere on the right-hand side. Thus, it's called phantom. And it's supposed to track some information statically about the data frame. Namely, we would like to track something about the schema. And in this presentation, we'll simplify it a bit, so we'll just talk about the column names. But in principle, this could be tracking much more, like even the type of the values in those columns. And so the way then that you would propagate this information is by making sure that whenever you handle a table, you actually keep in this type parameter, which we left out as sort of a hole here, information about the columns. So in particular, we would like to have some representation of the fact that this table has columns age and name. And we want this to be in the type level so that once we join this table, X's, with another table, Y's, we can actually deduce in the types that the resulting table will have columns name, age, and units. That's what you would expect for joining, right? You want the common column to show up once, perhaps in the beginning, and the rest of the columns to be essentially the concatenation of the two column lists minus the joined column name. And so in this presentation, we'll essentially step through an example of how you can encode this.
Mm-hmm. So the classical way to deal with this kind of information in the type is to use an HList. And this is very common in Scala. This is a definition using ScalaMatsuri enum, but it's very similar to what you would find in Shapeless, for example. And the idea here is, as Georg said, to keep schema information in the type, to track this information at compile time. And we will do this using an HList. So you can see here we have a constraint. So schema is a subtype of HList. And here the definition of a HList, it's very similar to a list. It has an empty case nil and a non-empty case cons with head and tail. The main difference between a list is that each element of the HList may have a different type. So it's called heterogeneous list. And this is why we have type parameter here, H and T, to keep track of this, this precision at each element of the list. So if you are working with an HList in Scala 2, this would be an appropriate definition. But to manipulate this type of list, you need to work with implicits. And this is really the canonical way of writing operations on this list. And so in this talk, we will talk about something else and another way. So we won't mention implicit anymore, but people who use this kind of structure should know that you can proceed from this definition and use implicits.
Right. And so without further ado, we'll actually sort of jump into the meat of this talk, where we'll be presenting two new solutions to this problem that try to improve on the status quo in some way. So we already said that with implicits, it works, but it might be a bit roundabout and perhaps not be very performant in some ways. So you might have seen compilation times go up. And so these two approaches are supposed to address those issues and a bit more beyond that even. So first, we'll cover match types, which is a feature coming to Scala 3. In fact, you can play with it now. If you use Dotty, you can actually start experimenting with match types. And hopefully, after having heard this part of the talk, you will also have a sense of how to use them, actually. So we'll essentially step you through how to solve the previous problem using match types. And then after that, we'll talk a little bit about some more sort of science fiction, if you will, that is subject to current research by the two of us. So this is something that we've, well, both the match types Olivier has been working on and a different version with dependent types that we've been collaborating on for quite a while. And so hopefully we'll give you some taste of where you could go beyond that and what you could do with even more powerful type of programming. But for the time being, we'll jump into match types. And so with match types, the way you would express this is by starting to build up your functions that you use to define the join operation. And so how could you do this? Well, the nice thing about match types is that they give you a way of expressing it in a very functional way. So you could define a type alias, concat, that we might want to use later to define join, because clearly we need to put together those two lists of columns. So we're going to define a type alias that has two parameters, x's and y's. And now we can use a match type, which is a match construct on the type level. It's very similar to the match you know from the term level, but now you can operate on types with them. So the scrutiny here is going to be x's. And if x is nil, then we want this to evaluate to y's. And if x is hcons, so it's a non-empty list, where we bind the head to lowercase h and the tail to lowercase t. We want this to reduce to, well, concatenate the tail with y's, so just a recursive call essentially, and then we wrap in the cons that has h as its first element. So what we have here is actually a rather straightforward definition, right? It's what you would expect to write in sort of the most naive, recursive, purely functional way. And with match types like this actually becomes feasible. So you can actually go away from the more logic programming oriented way that you would have to do with implicits. And there is a rather efficient way of evaluating this as well. So now, as an example, sort of how does this function behave? Well, it does hopefully what you would expect it to, but to give you an example, if you applied concat to h_nil and some HList L2, then this would evaluate to L2 because we matched on this part here, it's h_nil. So as a result, we reduce to y's, which would be bound to L2. And so if you look at a slightly larger example here, if we do concatenation of a one element list that contains only name and some list L2, then we evaluate down to, well, the concatenation of these two things. So a list starting with name and whose tail is L2. And so here you might be a bit surprised if you've never seen this. I'm using a string here, but at the type level. So this is called a string literal singleton type or string literal type. And this allows you to basically say, this is the type that corresponds not to all strings, but to this one specific string. So it's a type that's only inhabited by this one string, which is very convenient because what we want to do here is really operate in concrete values of strings. And so these literal types allow us to do that. And so this is actually a feature that has been around for quite a while in Scala, and people have used it successfully with implicits as well. But they come in really handy in this case. And later we'll see how to generalize from there further. One important note, though, is that this type level function, if you give it values where it does not know how to evaluate down, it will essentially just get stuck, by which we mean it does not evaluate any further, and you don't get to assume much about it. So if you're in a situation where, for instance, upon a join, you provided it types that were not precise enough to actually compute anything here, you would get stuck and you would run into a compile time error, which is what we want. And so there's a more general principle as to how this concat operates. So we have some rules. In this specific case, if you have a concat with x's and y's, it's going to evaluate to y's if x's is a subtype of h_nil, and it's going to evaluate to the second case if x's is a subtype of h_cons. But also, we can be sure that it's not a subtype of h_nil. It's disjoint from that. And why that's important, Olivier will tell you in some more detail.
Mm-hmm. So I think in this example, that that kind of precision I'm going to get to is not really important because in an HList, nil and cons are disjoint types. If you look at the definition, these are enums, so they cannot be extended any further. But in the general case, for instance, here with two traits, foo and bar, the situation is a bit more tricky. So here we are defining a type M that matches on T, and it tries to do a subtyping check against foo and then against bar. So M of foo evaluates to string as you would expect, because foo is a subtype of foo, the first case here, and it reduces. However, M of bar does not evaluate further. So again, it would get stuck in this state, and there is no way to simplify this type. And this might come as a surprise. You might expect M of bar to become int. So the reason for this is that the semantics of match types actually corresponds to the semantic of expressions, in that cases are evaluated in order, and in order to proceed or to evaluate past the case, we need to make sure that this case can never be taken. So to show this in a more concrete way, we have here a definition. We have here a definition of a function M that exactly mirrors the type that we have over here. You can see the syntax is slightly different because it's a match expression. So it uses underscore type foo and underscore type bar. And as you know, if you call this, this method, it will perform a type check at runtime. And so we cannot be sure that m of bar always evaluates to an integer, because we could call this method m with an object which is both a foo and a bar, in which case it would fall through the first case. So to say this differently, in order to rule out the case foo, we need to make sure that the type we are currently looking at is disjoint from foo. And in this case, we cannot prove that. And so we would simply get stuck on m of bar.
So with that knowledge in hand, we can now go ahead and actually define our missing operations. So remember, our goal was to define a type that corresponds to the resulting schema of a join operation. So basically, given two HLists containing the columns of both tables, we want to define some combination of type functions that gives us the join one. And we specified this to be essentially the concatenation of both minus the join column and then the join column up front. We'll show you again in a minute. But to get there, we definitely need one more type function, and so that's going to be remove. So concat we already saw. This is still the same definition. And now we also get to define remove. And in this one, you'll notice that the functionality for making stuff not evaluate, making it get stuck, is actually very important. So here we have remove that takes a first argument e, which is the element we want to remove, and some HList x's. And we're going to match an axis. And in case the list is non-empty and it contains the element we want to remove as the first one, we just return the rest of the list. That is, we've removed it. We're done. If, on the other hand, hcons falls through here and contains some element h that is not e, because it fell through, and some tail, then we remove the element e from the rest of the list, so with a recursive call, and then rewrap it in this const that we skipped over. And so you'll notice here that there is no case for nil, because we in fact don't want this to succeed for nil, for an empty list. In particular, remove should only evaluate down to the resulting HList if it actually found e and successfully removed it. And it's only going to remove the first occurrence. But that's kind of obvious because the schema will not have multiple columns of the same name.
Yes, and one important detail in this example is that the patterns in matches are actually case sensitive. So when you write hcons of uppercase E, like over here, then this actually matches against the type E, which is in scope. And when you use the lowercase syntax, like T, H, and lowercase t afterwards, this would be a binding, like you would use in, like you would see in values. So this is actually going to assign H and T to be the types of the head and the tail of the cons in question. And one detail that we omitted in this slide is that the parameters for concatenation and remove have to be bounded to be HList. And this is because if we come back to the definition of HList over here, you can see that the tail of the list here has to be itself an HList. And so for this code to compile over here, because when we concatenate, we call concat here, or we create a cons, all of these types are expected to be HList. So this is just a small detail. We kind of omitted it from the rest of the slide to make it shorter, but here is the full version. And now that we defined remove and concat, we're actually able to come back to the very first example. So in our very first slide, we did a join between age name and name unit to obtain name age unit. So the way to write this as a type would be, as we're doing in this slide, with type join. So the way it works is first going to remove the key from both table schemas with the remove here, and then concatenate that result, and finally prepend the key. So the operation that we wrote here actually mirrors what's going on in the Spark runtime. So it provides some additional safety when we use the join that is defined here as a method. And this is the join you would expect to see on the table type. So you can see in the result of join here, we use the join type. And this allows us to fill the holes that we originally showed you on the first example with tables, so that when you call a join operation, you actually compute at the type level the corresponding schema, and this will propagate through your program to gain some additional safety.
Right. So let's put this all together. Now we have all the primitives. Let's see what it looks like. So coming back to our initial example, we had a table X's and a table Y's, and we assume that these tables already have the right schema attached to them. So somewhere, when constructing these tables, we fed it some schema information. And in particular, here we have an encoding of the fact that the first table has two columns, one named age and a second one called name. And the second table has, again, two columns, but the first one called name and the second one called unit. And so in our join operation that we just defined on the previous slide, we assign the result type that is computing just the right table schema. So these will now carry the schema that says, well, there's a column name that comes first, followed by a column age and a column unit. And so now we actually have the static information to propagate this around the program in a rather straightforward way, right? All the definitions for this were not very verbose. And importantly, if we were to call this with something but name, so something that does not actually column in both of these tables, we would not be able to evaluate this down to anything useful. And so any operation later that relies on the schema is going to actually run into a compile time error. So we gained some significant safety. We actually know that this is going to fail at compile time.
Yeah, so I think this example is not fully satisfactory, because this kind of relies on the Spark runtime behaving the same way as the type we wrote. And so if we were to, I don't know, rewrite Spark from the ground up, we would probably want to go even further and use the same functions to compute the schemas at compile time and at runtime, or at least get some sense of safety that the type function and the schema runtime evaluation correspond to each other. So the way you would do this with concat, here I repeated the type that we showed you originally, and here is the function that implements concat on HList values and not types. So as we showed before in an example, we can actually use concat the type in concat the function whenever the matches corresponds exactly. So we really need to have a one-on-one mapping between each cases, have the exact same number of cases and the same return time for each case. And whenever all these conditions align, you're allowed to type your method as a match type. And so concretely, what this gives you is some form of dependent typing. And what we mean by this is that the return type of the concat function will depend on the type of its argument. And this is what we refer to in this talk by dependent types. And so this is possible with match types. So the example that we see here gives you exactly that. But it's unsatisfactory in a way because you have code duplication. So you see that even in this simple example, it's quite verbose to copy the entire match case. And this is the motivation for the next part of the talk.
So in the second part of the talk, we're going to talk about how to go above and beyond what we just showed you, how to fix some of the issues, and basically also gives you some taste of what else could be proven correct with low effort if only you had the right tools for that. And so we're going to be basing this on some form of dependent types that we're suggesting, or we have some proposal of how to integrate with Scala. And this is really active research. So quite different from the first part of the talk. You cannot actually use this if you play with Dotty now. But we are working on a prototype basically to evaluate these programs. And so now we'll essentially try to give you some sense of what would work in this kind of system. So what's the goal here? Well, the vision is to use term-level functions that we're already emulating anyways for pretty much everything. So rather than going through this duplication that we just saw with concat, you should be able to just define this concat once on the term level, where you have a strong notion of how it behaves and what it's supposed to do, and how to write clean, pure functional code, and then lift that to the type level in some sense. And that's to say that we would like to make it give you a very direct way of writing type level functions. And so how do we achieve this? Well, our proposal here is to use something called singleton types. So singleton types are a special form of types that we already encountered in the special case of the literal types that I showed you before, where we just said, well, the string name is a type which contains exactly only the string name. So it's a very small type. And that's why it's called singleton, because it contains exactly one value. And so you can extend this notion to any sort of term, or at least a larger collection of terms. And so, for instance, if you have a term like concat x's y's, its corresponding singleton type would be written curly brace concat x's y's, curly brace close, which is to say that the type of this expression is exactly what concat x's y's evaluates to. So whatever concat x's y's means, that's exactly what the type says, which is a bit silly, right? Because a priori, that doesn't seem very useful. And also, it seems like the most precise type you can assign to something. So how do you actually get anything done? I mean, you might as well say, well, a term is typed as whatever the term evaluates to. Well, we'll see in the following examples how we can actually use this to define very powerful and precise types. So the things you might have wanted to achieve with type level function before, you should then be able to achieve by using singleton types. And we'll add one important construct that makes this possible. But once you start actually writing your programs using these singleton types, you'll quickly run into one kind of trouble, and that is that everything has these ultra precise types. So it becomes very tedious to write even the result type for the simplest of functions. So to make this a bit easier and not go through the drudgery of repeating whatever you just wrote on a term level, and we add a new keyword that's called dependent, which lets you opt into precise type inference, which is to say that if I write a definition with dependent in front of it, something like dependent def, then I want its result type to correspond exactly to the implementation of that function, or some approximation if we can do that. But so first, we'll give you a taste of what that would look like.
Yeah, let's look at a concrete example. So we are coming back to the same thing, and we defined another list. This one is called LST, again with an enum, and we annotate both cases as dependent. What this gives us is the ability to refer to nil and cons in the type. So in Scala, if you write an enum, you would normally, after instantiating a list, always get type list in your variables, and this keyword here lets us lift these constructors to the type level. And then the concat is exactly the same function we showed you before with the dependent keyword in the front. And what this gives us here is the ability, when we use concat, to evaluate the body at compile time to compute the return type. And there is here, you can see a subtyping annotation. So this is required because of the recursion in concat. And it actually means that concat will always evaluate to some list, but at compile time, the type is actually going to be more precise than list, because depending on the input value, this match will evaluate differently. So let's look at a small example. Here we define two lists with A and B, do the concatenation, and now the compiler is able to infer the return type, or the type of L3 rather, which is exactly a list containing A and B. So you see here again use of the singleton syntax, and this means here that the result of concat is going to be exactly equal to the term that is contained here in these braces. And so in this first example, we actually get a perfect correspondence between runtime and compile time, because this code will do exactly what it says here on the slide.
Right. And so now you might be asking yourself, what exactly can I lift to the type level? What can go into this kind of singleton type? Well, of course, certain terms do not make sense on a type level. So stuff that is effectful, it doesn't really make sense because a type could be essentially relocated to any point. There's no really notion of time from before and after. So we don't allow you to put anything effectful in there. For instance, if you are trying to communicate with I/O, that's going to have to be handled in some different way. So first of all, the restriction on the subset of terms that you can put there is essentially the pure functional subset of Scala. So you can put all sorts of primitives there. So you can put literals. You can put data type constructors, in particular those that you annotated with dependents. And you can do pattern matching to actually extract information from there again. And of course, you can also do some other primitive operations like addition on integers and manipulating strings to some degree. What's important to note, though, is that the pattern matching is subject to many of the same rules that we just explained for match types before. That is, to make sure that this is actually sound, that it's safe, we have to sometimes not evaluate in the same way that it might have been unintuitive for match types, because we have to consider all the possible ways that values could be substituted for the scrutiny in the pattern match. And so as a result, if you think about the pattern matching in the singleton types, you have to think about them the same way that we thought about the match types.
So let's look at another example. In this small snippet here, we use the readString function in a dependent val. And readString has a side effect, so it will read input from the keyboard. So this cannot be lifted to the type. And the way we handle this kind of unsupported features is by using a new construct, which lets us approximate the terms that we don't support with an upper bound. So the syntax is up here. We write _t. And in this example, this translates as follows. So the resulting type here would be a list containing A. And as a second element, it contains some string, which is unknown statically, and finally a nil. So what we get from this construct is a way to talk about types inside singletons. So here in the last line, we are describing a term. And in the middle of this term, we refer again to a type. So we are really going back and forth between the two words. And the meaning of, so one way to understand this construct is in terms of non-deterministic choice. So we call this the choose operator, because it will evaluate to some value in T, which we don't know yet, and it could be any of these values. So what this gives us is some form of polymorphism. As we can see here in this example, we define the type of all the lists containing exactly 2 elements. And we can do so using the singleton type syntax, or in this case, it's a generalization of singleton, because this type doesn't contain a single value, but actually all the values where the first and second element of the list were picked out of any.
And the list has exactly 2 elements.
Exactly.
Right? No more, no less. Okay, and so now that we've explained to you sort of what the primitives are again, let's see how to put them to good use. So you can imagine how, well, we already saw how we could define concat with this, but let's go a step further. So I'll give you an example of a function that we might want to make safer. If you think of zip, the usual definition of zip that you know is a little bit unsafe, actually, because if you provide it with 2 lists where one is longer than the other, then it will sort of silently truncate to the shorter of the 2, which is to say that you drop elements from the longer list. They're not going to show up. So what if we wanted to define a version of zip that makes sure at compile time that you only ever call it with lists of the same length? So let's see how we could do this in this system. If you assume that the usual zip is called unsafe zip here, then we're going to define a wrapper called safe zip that is also going to take 2 lists. So the first parameter is going to be x's list, for instance, with this list definition that you saw before of an enum. And y's is going to be a list too, but it's going to have a funny singleton type. Well, this generalized singleton type, really, that calls size-like of x's. And so what's going on here? Well, the intention is that singleton size-like of x's is supposed to be all the lists that are exactly the same length as x's, but with arbitrary values in them. And so let's see how we could define size-like. Well, we would make a dependent def, so it can be used in the singleton type. It's going to take x's as a list, and it's going to return some sort of list, but this is just a bound. And so we're going to match an x's. And so what are all the lists that are exactly the same size as x's, but with potentially different values? Well, if x's is nil, then there's only the nil as well. It's only the empty list. However, if x's is non-empty, it has at start one element x followed by y as its tail, then, well, it's going to be a list of at least one element, and that element will choose from any. It could be any element, right? Because we want to allow all the lists. And its tail is going to be chosen from all the lists that are the same size as its own tail. So that's a really straightforward definition of what it means to be a same size list, right? And the nice thing is that now that we've written down this term level definition of what that means, we've essentially written down a generator function, right? It's a term level generator, really. And so we can use this generator to describe a type. And so you see how with very little effort, we were able to describe a rather strong safety property. So now we have a safe zip version that actually will only accept lists if they're the same, provably the same length. So again, you can actually rule out a whole class of errors at compile time. So I hope you found this example very motivating, like we do. We've dedicated a lot of work to this. And so if you're interested, there's some more resources. First of all, there's documentation on the match types in Dotty. That's something that you can use right away. And we'd be excited to see what you come up with. And on the sort of more advanced work that we've been doing with singleton types and dependent typing, we have a paper draft. So that's something that we've been sort of doing active research on and prototyping. And if you're interested in sort of the gory formal details, then feel free to check out this paper. All right.
Thanks a lot for listening. And we'll be happy to take any questions.
ヨルグ・シュミットさんとオリビエ・ブランビランさん、発表ありがとうございました。皆さん、拍手をお願いします。
Merci.
Merci.
質問がもしあれば、1問程度お聞きしてみようと思いますが、何かございますでしょうか。今、書き込み中とあるので、しばらく待ってみようと思います。一つ質問が来ました。この機能、これは、ディペンデントタイプの話だと思いますが、スカラのバージョンいくつ頃に入りそうですかという質問が来ています。
Yeah, so that's a very good question. I think so the question, if I understand it correctly, is what version of Scala is this feature likely to be in? So the match types are definitely coming. They're essentially there if you're using Scala 3, so you can start playing with them right now. The thing we presented in the second half, the dependent types with the singleton types, that's science fiction, I would say. So it may or may not come at some point in the future, but really this is research work. So there's no, so it might not come. Most likely it won't.
Maybe in the next language.
Maybe in the next language.
ありがとうございます。もう一問だけ来ておりますのでお聞きしたいと思います。新しいディペンデントキーワードとトランスペアレントキーワードの関係性を教えてくださいと。すごく似ているように見えますがということです。
Thanks for your comment. So the question is, can you describe the relationship between the dependent keyword and the transparent keyword? So how do they relate? And yes, so what we have in Doti is based on inlining currently. So I'm not sure in what is today in the compiler, but I know that at some point we had a way to recompute the type of functions after inlining. And so there are some similarities, but I think the fundamental mechanism is really different because it's all based on inlining and it's all about recomputing types, whereas in our case, we really have evaluation on the type. So we manipulate the types and they let us describe more types. So for instance, the size-like example that we showed at the very end, there is no inlining going on. It's purely a way to describe a set of values using dependent types. And I think this is where the main breakpoint would be between the two approaches.
I hope that
ありがとうございます。では、以上をもちまして、このセッションを終了いたします。ご視聴いただきありがとうございました。最後に盛大な拍手をよろしくお願いします。